Consider a fluid dynamics simulation. While the surrounding particle field distorts chaotically, a distinct geometric subregion remains perfectly cohesive, trapped within its own boundaries. In linear algebra, we represent systems like this using a linear transformation, denoted as T, that maps a vector space V back into itself. When you apply T to the entire space, the vectors generally scatter. They are pushed off their original axes, distances stretch, and the initial geometry is scrambled. This creates a structural problem. How do we locate isolated subregions within this space that are completely self-contained? Regions where every vector inside is mapped directly back into that exact same region. Identifying these closed loops, known as invariant subspaces, allows mathematicians to break down highly complex, multidimensional operators into independent, manageable pieces. The formal architecture for doing this is laid out in Kenneth Hoffman and Ray Kunze's Linear Algebra textbook. Written for MIT students in 1961, this curriculum shifted the pedagogical standard. It moved undergraduate mathematics away from brute force matrix calculations toward pure structural abstraction. We will use their exact framework and examples to dismantle the geometry of linear operators. Mastering invariant subspaces lets us treat a linear operator not as a static table of numbers, but as a set of structural relationships. We start with a finite-dimensional vector space, V, and a linear operator, T, acting upon it. Inside V, we define a smaller subspace, W. This is a 3D coordinate system containing a flat 2D plane designated as W. Notice the vector alpha sitting perfectly flat on this plane. For W to be considered an invariant subspace, applying the operator T to alpha must result in an output factor that also lives exactly on this plane. The formal notation for this requirement is T of W is a subset of W. We apply the transformation, and while the vector changes length and direction, it remains locked to the two-dimensional boundary of W. The vectors inside the subspace are not frozen in place. The transformation still moves them. They simply cannot escape the plane. Because the boundaries are closed, we can isolate this region. We treat W as its own independent, smaller vector space, operating strictly under a restricted operator, TW. To see how this works in practice, we look at the simplest possible iteration, the one-dimensional invariant subspace. This requires the standard definition of an eigenvector, where the transformation of a vector alpha equals a scalar multiple, C, of that same vector. Here is a 2D plane, featuring a single vector on a one-dimensional dashed line passing through the origin. When the transformation is applied, the vector scales, but its direction is perfectly preserved along that specific line. Because the output is just a scaled version of the input, the transformed vector never leaves its original axis. The line itself operates as a closed system. Eigenvectors are entirely synonymous with one-dimensional invariant subspaces. They act as the base case for the theory. However, many operators do not have enough eigenvectors to span the entire space. To analyze those systems, generalizing this concept to higher dimensional invariant subspaces is required. We translate this geometric property into algebra by asking, if we know a subspace W is invariant, how does that actually change the matrix representing the operator T? We select an ordered basis specifically for the invariant subspace W. Then we append additional vectors to that set until we have a complete basis for the entire space V. When we write the matrix for T relative to this specific basis, we generate a distinct block structure. The upper left quadrant is filled by a submatrix we call block B. This block represents the operator acting solely within the restricted boundaries of the invariant subspace W. Directly below it, the lower left quadrant becomes a block of absolute zeros. This gives the overall matrix a block upper triangular form. Those zeros are the algebraic manifestation of invariance. They show that any vector originating inside the subspace W stays within W, never leaking into the other dimensions of the full basis. Because the determinant of a block triangular matrix is simply the product of the determinants of its diagonal blocks, the characteristic polynomial of submatrix B becomes a literal factor of the larger operator's polynomial. In other words, FTW divides FT. By identifying invariant subspaces, we expose the hidden geometric architecture of a space. We then use that architecture to slice complex matrices into manageable triangular blocks. Hoffman and Kunze pressure test this theory by pushing it beyond standard geometry and into pure algebra. In example 6, they identify the trivial invariant subspaces. For any linear operator, the entire space V, the zero subspace containing only the origin, the range, and the null space all satisfy the condition of invariance by definition. Example 7 shifts the environment entirely. Consider the vector space of all polynomial functions over a field, and let the operator D represent the process of taking the derivative. We define the subspace W as the set of all polynomials with a degree of n or less. Applying the differentiation operator to any polynomial always decreases its degree. If you start with a polynomial inside W and take the derivative, the output is structurally guaranteed to remain within the degree boundary of W. Invariance is not restricted to rotating physical vectors. The property holds perfectly across the logical boundaries of any rigorous algebraic system. Example 8 introduces commuting operators. If a linear operator U commutes with T, meaning T times U equals U times T, then the range of U is automatically an invariant subspace under T. We can prove this algebraically in one line. If a vector alpha is in the range of U, it equals U of some vector beta. Applying T gives us T of U of beta. Because the operators commute, we swap them to get U of T of beta. Since the outer function is U, this output fits the exact definition of the range of U. Example 9 provides a negative case. Consider a linear operator representing a rigid 90-degree rotation in a standard two-dimensional plane over the real numbers. Every single non-zero vector in the space is pushed off its original axis by the rotation. Because no vector maps back onto its starting line, there are 0 one-dimensional invariant subspaces in this specific real number system. The existence of an invariant subspace is never guaranteed. It depends entirely on the behavior of the transformation and the properties of the underlying scalar field. We started with a chaotic vector space subjected to a transformation and established the mathematical rules required to isolate stable ecosystems within it. An invariant subspace remains strictly closed. The operator acts on the space, but the outputs never breach the defined borders of the subspace. The familiar concept of eigenvectors is simply the one-dimensional foundation of this broader geometric truth. This geometric truth dictates algebra. It allows us to select bases that force complex matrices into simplified, block triangular structures. Isolating these subspaces provides the entry point for simplification. By locking down an invariant subregion, we reduce the space's complexity, turning an entangled n-dimensional problem into smaller nested equations. If you found this breakdown valuable, like the video and subscribe for more rigorous explorations of linear algebra and structural abstraction.